Okay, introduction to Le Chatelier's principle. Le Chatelier was looking at equilibrium and seeing that once you have something at equilibrium, if you change it, how does it go back to equilibrium? So this guides us in predicting the effect of various changes you can have on position. If a system is disturbed, the position of equilibrium will shift to minimize this disturbance. That means those concentrations are going to change. You don't go back to the original equilibrium position, you get a new one. So, couple examples. Closed container, ice and water at equilibrium, temperature's raised. Well, if we increase the temperature, that means there's going to be more liquid water because there's more energy involved. This is an endothermic reaction. Okay? Ice melting is endothermic. It takes energy in to make liquid water. The system temporarily shifts to the right to reach a new equilibrium, a change in amount. Another example, closed container of these is at equilibrium. We add more NO2. Because we have more of this, it's going to shift it towards the reactants. Because I have more products that can react to make more reactants, temporarily shifts to the left. Another example, closed container, water and vapor at a system. We remove energy. When I remove energy, that means I'm going to have, so we're going to remove vapor from the system. When we remove vapor, that means there's more water and energy present to where it's going to shift to the right to make more vapor. It's true with vapor pressure. When we remove the vapor that's above it, more and more of this liquid, in this case water, is going to evaporate to have that equilibrium vapor pressure. Another example, closed container, the pressure is going to be increased. Now in this case, we have the idea that we have two particles on the right side, one on the left. The system is going to temporarily shift to the left to reach a new equilibrium because there's a fewer number of moles of gas on that side of the equation. Think about it, if we increase the pressure, that brings them closer together, a decrease in volume, of course. And so this could be more likely that NO2 particles are going to collide than this one particle is just going to split. So that's why it's going to have an increase in N2O4. Let's look at some other effects. So volume changes on equilibrium. Increase in pressure will lower the volume. The equilibrium will shift to the side that has fewer moles of gas particles. This helps relieve the pressure. So if we have an increase in pressure, there's more moles of gas, more particles that are going to be compressing than the 2 moles. This would shift it to the right to make more products. What this really does is that it increases the forward reaction and increases the reverse reaction. But due to the fact that 4 is becoming 2, the increase of the forward reaction is going to be higher than the increase of the reverse reaction, so the overall net gain would be a shift to the right to make more products. The effective volume changes on equilibrium if we decrease. This will go towards more moles of products. Again, the idea is that both will be decreased, but because of the fact that this is 4 particles, this decrease will be a higher decrease than this one, which means there'll be a net gain of shifting it to the left, making more reactants. Let's look at this in a graph form or reaction progress. So it's at equilibrium. It's all good. We're going to add some N2O4. Some of it's going to decompose to make more NO2. So we added some more. Now K and Q are not the same. This is going to start making more NO2, start using up some of that N2O4 to produce a new equilibrium, different than what was there before. Now you can see it's at a new equilibrium. Same value, but different amounts. Okay, different amounts. Let's say we added some NO2. Some of it decomposes to make some N2O4. Again, spike up. Not at Q, changing. Now it's at a new equilibrium, newer than before. Different values, but again, same equilibrium expression, new equilibrium. Now temperature, So temperature changes can affect the equilibrium constant as well. It kind of depends if it's endothermic or exothermic. So let's walk through an exothermic one. So taking heat into the system, right? That's what we think about as endothermic. Energy plus the reactants makes a product. Now in this case, we got sugar, so it's 1 over the reactants. If we increase the temperature, there'll be more energy to react the reactants. This will decrease the concentration of the reactants, therefore KEQ will increase. Decreasing the temperature causes the reverse reaction, making more CO2 and H2O, therefore KEQ will decrease. If it's exothermic, heat's leaving the system, like a synthesis, we're making methane and energy, we have the given possibilities, right, as our reactants and products, reactants over products. If we increase the temperature, then there's more energy to break down that product, which means that there'll be less CH4, more H2, therefore KEQ will decrease. Decreasing the temperature will remove the energy, making more CH4, less H2, not which will raise the KEQ. So you have to look at it from the holistic standpoint. It's not just exothermic will increase and then decrease. Look at how it's going on with each of these. However, we keep in mind that if we're adding energy to either side, that's going to further pushing it the other direction. So in adding energy, the reaction is going to be pushed away from energy. If we decrease the energy, cooling it down, it's going to come back towards the side of energy to make more of it. So it's ironic that when you remove energy from the system, you actually generate more from the system, from the chemical bonds. All right, that's it. Lucky you, but wait, there's more. Just a little bit. So catalysts, be careful with this. They are an alternative, more efficient mechanism, works both forward and reverse. The effects are for forward and reverse by the same factor. Therefore, they don't change the position. They don't change, you just get to equilibrium faster. Much like if you have the idea of I'm hungry, I'm fed, cooking food may take a while to get me there. Other ideas, when we think of this, may get me there faster. Restaurant order, pay the delivery person, boom, I'm there faster than it did to cook it. All that does is catalyze it, change these different activation energies to get me there faster. All right. Come in with any kind of questions. Talk to you later. Take care.